Hello, everyone, and welcome to this talk from our Resilience of Autonomous Systems seminar series. Today's seminar will be presented by Xinwei Fang, who is a postdoctoral research associate working on the Trustworthy Autonomous Systems node in resilience. Xinwei received his PhD in computer science from the University of York. He has worked then as a research associate on several interdisciplinary projects, including the Assuring Autonomy International Program. And his current research focuses on mathematical approaches to reducing uncertainties and disruptions in autonomous systems. And in today's talk, he will cover recent results from his research in these areas. Whenever you are ready, Xinwei.
All right, thanks, Reddy. Yeah, today I want to use this opportunity to share with you some insights that I gained through my past research on how we can develop a trustworthy autonomous system through understanding and mitigating uncertainties. So autonomous systems are becoming increasingly important in our daily life, but what do we exactly mean by autonomous system, and how is it different from an automated system or automatic system that we have seen in the past years? So in my definition, an autonomous system is expected to adapt to unexpected changes without human interventions, whereas the automated or automatic system can only adapt to expected changes. So let's considering a simple example, a water kettle. It boils water and automatically switch off when the water is boiled. So it is perfectly reliable for that specific task. But however, if you ever try to put milk in that water kettle instead of water, then you quickly see why it is not an autonomous system. The water kettle is not able to adapt to this unexpected changes because the milk and water has a different boiling point, which is not predefined in the design time. In the contrast, the autonomous system is designed to handle such unexpected events and to adapt accordingly. So for example, an autonomous car must be able to react to unpredicted road conditions or different weathers. An autonomous servicing robot must be able to handle users with different behaviors, such as those who have special needs or interact with robots unexpectedly. And an emergency respondent must reliably respond to an emergency, which can be unexpected and require quick decision-making under such challenging conditions. So, despite we've seen many successful deployments of traditional complex and safety-critical systems, the developing a trustworthy autonomous system still remain an open challenge. There are several reasons for this. The first, autonomous systems are fully data-driven, and they start sensitive to the quality of data input. Additionally, since there is no longer a human in the operation loop to safeguard such a process, ensuring the quality of the data input is even more challenging. Second, due to the complexity of the autonomous system and increasingly use of AI components, uncertainties from upstream of the process can be nonlinearly propagated, resulting in small errors have a large impact on the system behavior. This makes understanding, predicting, and mitigating uncertainties increasingly difficult. Third is, as prevention is always better than cure, autonomous systems are expected to proactively adapt to changes to avoid a violation of requirements in advance. While this can have a great benefits in terms of reduced maintenance or fixing costs, the realization of such approach remain challenge. And finally, autonomous systems are expected to have a broad range of applications, but each application will have a unique context and use scenarios, making generalization of such development strategy difficult. Right, so let's take a look about how current autonomous systems are designed and the philosophy behind their design. Here it shows the 3 design models. The first one is called OODA model, which is widely used in military applications. The second one is a MAPE-K loop, which is widely used in software control system and self-adaptive system. And the third one is so-called SUDA model, which is created by borrowing ideas from OODA models and was developed as a part of Assuring Autonomy International Program. So when we look at these three models, we can see the similarities. That is, their concept of creating an autonomous system workflows are very similar. It requires a observation, processing, making decision, and action. So to design an autonomous system, we first need to look at obtaining a knowledge that well facilitates such a process. This typically starts with understanding the operating environment in which system will be deployed, including the type of changes that may occur in the environment. We also need to determine which sensors are appropriate to use for such conditions. We need to make sure the sensor is capable of using in the given conditions. And we need to understand what data process methods are necessary and to extract the relevant information from the sensory data. So once we have data, then we need to verify its validity and the correctness. So in traditional systems, the human would be involved in this verification process. However, for autonomous system, we need a verification engine to verify this information, and we need to understand the criteria for the verification of the system behaviors. So finally, we need to make a decision based on the verified information. In decision-making model, these decisions can be made either by humans or a system itself, depends on the nature of the application. So for example, in our autonomous systems, that is observing information from the environment and making suggestions for humans to make the final decision, then the decision will be made by the human, but the autonomous system will provide the processed information to the human. In contrast, in a servicing robot, then the decision of whether to administer the medication to the patient is fully made by the system itself. So throughout the design process, uncertainties may arise from the environments or the sensors used. This uncertainty can propagate through the entire process and through the verification steps and impact the decision-making process. So in the later part of this presentation, I will provide some real-world examples to demonstrate how uncertainties can arise at a different stage of the process and how verification engine may help to mitigate some of the impacts. Right, so give you some the context of the first project that I've done in the past. This was a project, EU-funded project funded by FP7 project. The aim was to monitor the urban air quality in cities. And we've looked at the problem we were thinking about how we can better monitor the urban environment. So by the time, there was two major means of monitoring air qualities. One is using a high quality monitoring instrument, look like this bunky red-green boxes. And it very expensive device, cost like 100K to 200K annually. And we only have 9 of these sites around York. Because of the price of it, we cannot afford more than that. This type of devices provide a very high temporal resolution. So they provide the data hourly, but because the cost of it limits the spatial resolution where this device can be placed. On the other hand, we have another low-cost solutions, which is they call the diffusion tubes. So this is just the tubes left there for a couple of months, then manually collected, sent to a lab for analysis. Each of these devices are very cheap, probably £5. So we can afford to deploy a lot of them. The problem is this requires manual deployment and collection and analysis, which prevents how frequently they can be redeployed. So we roughly have 350 of them around York. And if you can see, it's actually along the major road of York. So the problem of the current, So the problem of these solutions is they have either very limited spatial resolution or temporal resolution. Then we start considering whether we can use a new technology to bring up this problem. So we started thinking about using a local sensors. The low cost is relatively to the high quality instruments that's cost 10,000 Ks. So each of the sensors cost around £3,000 by the time. So they were produced by Perkin-Elmer. They were either can be battery or main powered, so they are versatile. It can be mounted on the lamppost if the manpower available, or you can just plug in a battery and a solar panel. It will work for a period of time. Then they are designed to have a lifetime of 18 months, just because some of the sensors, they use a chemical that degrades over time. They use GSM to communicate and to store the data in the cloud. And they also have onboard storage where they can temporarily store the data where the communication were not available. And they were taking 8 monitoring parameters, and they will all have a 20-second sampling frequency. That is, for each minute, we have 3 readings for 8 of the parameters. They were NO2s, ground ozone, NO, temperature, humidity, VOCs. Dust is the particulate matters that's smaller than PM10. So if a PM1, PM5, they all consider as dust. A noise level is just the dB values. So we actually had a deployment in York, and we deployed them in 2 completely different environments. One we consider a harsh environment. We're located in central of York next to a busy junction. They call it Fishergate. And you can see Fishergate is actually located here. It's one of the major roads coming in and out to York. And another one is WACO, is Wolfson Chemistry Lab. It's actually on university campus, away from the major road. And if you see that, it's all the green area, so we consider the conditions relatively mild. So the ALMA sensor were co-located with a reference instrument, and this instrument was actually a high quality instrument that managed by York City Council. And we have another one which is managed by the chemistry department to treat. We use those reference sensors as a reference to see how the ALMA would behave. Right, so during those 12-month deployment, we actually identify quite a large number of sources of uncertainty, and we will just talk about what they were. Right, the first one is the environmental interference. So if you look at that, the table that shows how much data that we are expected to receive actually received. So that's, we're doing a period of a month, and we have about 9 sensors and each ID. And because we know in each minute we have 3 readings coming in, and we can calculate how many % of reading were actually successfully received during that hour. And this is shows in the color plot. So for the 100% in during the period of time where we have all data received, but we see a clearly data gap in those 2 days where we almost have 0 readings at all. And we actually look into the investigation, what was the issue, and realized those periods actually co-located with the university open days. Remember, the ALMA sensor was required a GSM communication to transmit the data to the cloud. Just due to that hour, our suspicion was they were so crowded and jammed the transmission station will leave a large data gap during that period. And we also see the high spikes in the data after its recovery. And we're looking into the root cause of it is because we have an onboard storage that we previously mentioned. Once the data is recovered, it will send a single package to the cloud. And the cloud was thinking that's with single reading. So it accumulates all the values into one, so make an extremely high spike after recovery. So we see that the environment interference, which is unexpected, will actually have a data gap and a spike in the data set and affects the quality of the data. Right. And the second one we identified was a normal but unusual event. And if we think about the ALMA sensor that co-located with the reference instrument in the Fisher gate, and if we box plot the readings, we see extremely high outliers appeared in the ALMA sensor, where in the reference sensor, they looked more normal. And if we average the values annually, then the ALMA sensor was just above, significantly above national average NO2 limits, where the reference sensor were below that bar. And that was the reason we were asked by the York City Council, we're not allowed to share the actual physical units about the readings. So this is just a mask, but the pattern of the two sensors were cross-comparable. So if we look at the cause of that, because the ALMA sensor have a higher spatial temporal resolution compared to the reference sensor. Reference sensor is only got 1 hour reporting rate, where we have 20 seconds. And the thing is, when the diesel bus idling next to the sensor, it will have an extremely high spike. But that's only lasts in a short period of time. If you're not familiar with York, if not familiar with Fisher gate, I can illustrate from this map. So the Fisher gate is actually this area, and the sensor, ALMA sensor and instruments were co-located in this area, in the shadow. So the main road is here. So for the bus one entering the center, they need to give away for the main road, more main traffic. So the bus will queue around this line, which is right next to the sensor. And that's why we, in the certain time of day, especially a rush hour, we can see a high spike of the ALMA sensors. And that, of course, is the problem. In a traditional way, the people would just standard procedure for processing the data is just a manual screening. So it will employ a human sitting in front of the in front of the screen to manually select the abnormal values. If they find that is suspectly high, they would just remove it without any justification. And we will see that a real but normal but unusual events well causes spikes in the data and causes data issues and concerns. Right, and the third one is the errors and the mistakes that we had during the deployment. And this is an example of the Fisher gate deployment where we using the metal boxes to cover two ALMA sensors just for security reasons, but at the same time, those metal cages behave like a Faraday cage, blocks all the signal that transmitted to our cloud. So we have a completely black cloud for 2 weeks, and we have to find a reason why was the cause. And also we find some spikes, very unusual spikes, and we're looking into the deployed sensor, we actually find spiders start living in those sensors. That may cause the problem. So a frequent maintenance probably needed for the sensor being deployed, and we need to make sure they are deployed as intended. Right, so this fourth one is actually a lack of knowledge. I'm thinking about the calibration of data because we have a sensor co-located with a reference sensor. Ideally, in a perfect conditions, that is for each unit of reference sensor reports, the ALMA sensor reports the same unit. Then it will perfectly in a linear as just a rate of 1. That's rarely be the case in practice, but ideally we want to see a linear trend between two, or nonlinear trend or functional trend between the reference and the ALMA sensor where we can calibrate them. But in reality, this is the data that we managed to see. If we see the y-axis is the value of the reference sensor produced, and x-axis is actually from the ALMA sensor. And compared to the Fisher gated deployment and Waco deployment, we actually see there is no linearity here at all. Then making a calibration of this data even more difficult, and to understand what's the cause of this issue, we actually spend a lot of time. So we started to work with the developers to figure out what exactly is the problem, because all sensors were passed the quality check, and realized that in the quality check, they create the vacuum environment and they place the sensor in that environment, only inject the given amount of pollutants, one at a time. So the sensor will provide a reading and compare with actually controlled injection. You will know how good the sensor are. But in real practice, the sensor were exposed to the air. Then air is actually composed by a different type of substance. Then a type of sensor will sensitive to multiple substances, making this data miserable. So for example, the NO2 sensor is cross-sensitive to the ground ozone. If ground ozone level is high, then its sensitivity to its original NO2 will have a different rate. So we have to correct that if we understand that problem. So after finding out, we'll actually be able to correct some of the patterns and make the sensor usable. Right, so the first thing we have to look at is the problem, the source of uncertainty introduced during the environment. Then we're looking at how the uncertainty can come from the processing of the data. And we consider there with three ways. The first one is the classification accuracy, because classification is a method that has been widely used in current AI system or autonomous system. They're widely used, for example, in autonomous cars. They were used to classify whether the object in front of us is a human or a bus. Where in a servicing robots, the robots may need to classify whether the user is happy or unhappy. So in traditional way, the classification will have two classes, and found the gap, find a single model that be able to divide the whole number into two perfect classes. This is ideal situation, but in theory, we never encounter that situation. We always have a misclassification in these scenarios. But in practice, they look even more nasty. So if you're looking at this, we can see the blue dots is dominant at the lower parts, where orange one is dominate upper. But if you were try to find a single model to classify those two, it's particularly difficult left without no errors. Then how we can deal with these errors and how the errors made here will impact the system level behavior. That's why we believe the verification engine is important to manage this and mitigate the impact of these errors. And secondly is the context is important. As we just mentioned, the classification error is highly avoidable in practice. And we've seen that if we try to using a AI component to identify a speed sign, then not all errors have the same impact. So for example, if we true label is 30 miles an hour and we incorrectly label it to 120, it's definitely have a larger impact than if we misclassified a 60 label to 50, where because the 10% speed variation is often allowed in practice. So we see that this is, so we see that the error will have a different impact, and this need to be carefully handled by a verification engine. And that also highlights why a verification engine is important in this context. And also we start to see an increasingly use of AI methods, and they were inappropriately used. For example, if we assume we're in a pub quiz, then we were asked a question now, what is the largest country in Central America that isn't Mexico? And if we were using the ChatGPT as a information supporting tool, aka cheating, then it will actually give a different result. So for example, it says the largest country that isn't Mexico is Nicaragua. Then second is telling me Mexico is not actually in Central America rather than North America. Then the third, if I change the way of asking question, is actually giving me a different countries. And it's actually thinking about the AI is actually always providing information for us, and how we can use this information wisely is a challenging task to take. And that also shows the importance why a verification engine is important in this case, because it needs to manage and mitigate the impact of misleading information provided by AI. Right. So talking about the verification engine is important, but what exactly a verification engine is? We consider verification engine as a component of the system that is responsible for ensuring a system behavior complying with its intended specification. And using this as an example, so we consider a behavior of system be able to modeled by a stochastic model, for example, Markov model, and the requirement of the system be able to encode it in probabilistic temporal logic. And by taking those two inputs, a well-known verification engine, which is probabilistic model checker, will output a true and false to give you whether the current, whether the requirement is violated or not. And this is all important at the runtime, as stated in this paper, because the runtime conditions change all the time, and we need to keep monitoring the changes and update the models to see how the violation is how and when the violation is likely to occur. Right, so since the verification at runtime are important, we're looking at how we can build a better verification engine. And since the probabilistic model checker is a good example, we continued in that such a way. So we consider the verification engine need to be runtime efficient. Otherwise, the system may take hours and hours to evaluate current violation for requirements rather than taking rather than to perform its own task. So if we see the system freeze there and doing nothing, it probably doesn't got a runtime verification engine. And the ability to analyze a complex system is also important, because we've seen an increasingly complex autonomous system are needed in different applications. For example, the self-driving cars, they are very complex to consider the sensors, the processes, everything. The system will be big and complex, and current verification engine will just not be able to cope. Then the lastly is we want a verification engine be able to proactively verify the system and allow the system to proactively adapt to changes. That is the ultimate goal for us. Right, to talk about the probabilistic model checking, it is actually one of the mostly used verification engine in this context, because they capture key aspects of the real-world system and processes, and they'll be able to support the analyze of the wide range of properties of interest, including performance, dependability, reliability, safety, and cost. And they will enable the principled decision-making in such autonomous systems. And we just to give an example on how the probabilistic model checker works. So imagine there is a system and its behavior be able to encode it as a stochastic model, such as discrete time Markov chain model. And they would just states and transitions and probabilities. And for this DTMC model, we actually can inquiry some of the probability of reaching certain states. For example, the probability of reaching states of can be calculated by 0.85 multiply 0.85 equals 0.7225, where we can query what's the probability of reaching final state done. So if we are considering the states of here associated with the fail of a given task, then this 0.7225 is actually associated with the failure rate. And to further reduce the failure rate, we actually be able to know those are two important values to make such reduction. Then if we have any means to reduce those values, we'll be able to reduce the failure rate. But the values often not available at the design time, and they often changes at runtime, and that's why they start to use a parametric model checking. So the system now becomes the parametric DTMC. So instead of having values on the transitions, when those values were not available, they used a parameters to replace the values. Then calculation is also similar to the previous examples and straightforward. For example, if we query what's the probability of reaching state of, or what's the reward value of reaching state of done, then instead of having a single values, it will generate a closed form algebra formula. And this is with just respect to what parameter we used in the model. So this process is now be able to fully automated by leading probabilistic model checkers, such as Param, Prism, and Storm. And the closed form formula derived from existing parametric model checker are extremely useful because they only need to compute it once and can reuse many times as long as the structure of the system remain unchanged. They can help to avoid surprise values due to nonlinearity between verification points, because we know how each step the increments using based on the expression here. They can find a minima and a maxima because those values are often associated with a best or worst case scenarios, and we can perform a better analysis in such a way. And we can analyze the sensitivity to different system and environment parameters, and also solve equations. For example, if we have a hard requirement for off, we know what's the best option for P and Qs. Right. So despite the parametric model checker have so many benefits, their usability are still very limited. And for example, for a system which is modeled like this is a foreign exchange system. Thinking about this have two modes, then at once enter different modes, it will have to make a different decision to how to trade the foreign currencies. And if we will extract this workflow into a DTMCs, it will only have 29 states and 58 transitions and have 24 parameters, just like showing on here. For the existing parametric model checker, we're not able to produce the algebra expression for such obvious small systems. And for the even smaller and simpler systems where PMC is able to obtain the algebra expression, they are often extremely long and complex. So given example, this is using Storm to derive the algebra expression for a system model which only have 17 states and 34 transitions with 17 parameters, then the algebra expression would just look like this. But it has 35,000 operations, and each operation is just how much multiplication sign here. This probably only got 100 of them, and we have 35,000 more in this. And you can imagine how big this file can be. And when you evaluate this large expression at runtime, it will take a lot of computational resources. Right, so as we've identified the problem, one of that is the efficiency of the PMC, and we come up with a parametric model checking, a solution for parametric model checking via fragmentation. And this piece of work was done in a part of the Reason project. And the idea was simple and straightforward. So thinking about if we have a DTMC that's too large and complex for the current PMC to be analyzed, then if we query what's the probability of reaching final state, then instead of taking hours and hours waiting FPMC to return the results, we can proactively decompose the large system into a smaller DTMCs, or which we called fragment. So for a sub DTMC from this one, we call it as a fragment. Then once we determine the one fragment, we're looking at what is outgoing transitions, which is connected to all the part of the DTMC as a reward, as a reachability property. Then we input this smaller fragment into existing PMC, we'll derive the updated fragment to the output values. Then in the original ones, we just replace the entire fragment with a single node and update the new transition probability based on the result of the model checker. Then the next steps, we just find more fragments and doing the same thing and find even more fragments until no more fragment can be found. And once we replaced all the fragments with a single state, we end up with a much smaller much smaller model, which we call the abstract model. So this is original model. Then we put this abstract model using original PCTL properties to calculate through the parametric model checker to calculate the abstract formula. Then the combined, that is the fragments PMC formula plus all the abstract formula would just equivalent to extremely long single fragments that we've derived in a traditional parametric model checking, that is inputting the entire model and the requirement through the system to derive a result. So having said that, we call this as a faster parametric model checking. The process called it as faster parametric model checking. The theoretical foundation was first proposed in the TSE paper. Then in that paper, the fragmentation will rely on domain knowledge. That is, the human has to give an input of how to fragment, how to make a fragmentations. But for this work, we've automated all the process, increased the scalability of the fragmentation. So for given DTMC, we will automatically process the fragment and compute the FPMC closed form models. So FPMC improves the runtime efficiency of the existing parametric model checker and allows the analysis of much larger and more complex system, as we shown in our published papers. Right, so another advance that we want to make in this area as a verification is to have a proactive adaptations possible, because the prevention is always better than cure. As again, this piece of work is done within the Reason project as well. So we take advantage of having a parametric model checker. So we have two stages work. The first one is just having a model itself and a requirement through a parametric model checking. This can be also through the FPMC that we just described. In that case, we'll be able to handle a larger models and to derive the algebra expression. And the reason why is in the design time is this parametric model checking is very time consuming, and we actually can afford at the runtime because we often have more computational resources. Since this is reusable and at runtime, we do not need to recalculate the values. So at stage 2, we take advantage of this algebra expression in the disruption prediction engines. So at the runtime, we actually monitor all the parameters, P1, P2, and P3, and we will take the history data of them and using the history data to predict the future values of each parameters. Then we can use the predicted value propagate through this algebra expression to calculate the changes, to calculate the future system level properties as shown here. So over time, when we have a prediction of all the parameters, and we can actually see how the system level property, the trend of the system level property over time. And we actually see the violation for requirements at this particular time because it's below our requirement 0.8. So given example of how this can be use to consider a very simple example, that is a food picking robot. So thinking about a robot moving around in a farm, then it would just do a task that is picking a fruit. So for each starting it well positioning itself at the right location, ready for the picking, its success will start the picking. If the picking fails, it go into the decision stage where either repositioning itself to make it picking, or it give up such a picking and go to an next fruit. Or it may not be success, or the picking of success is collected the piece of fruit and finishes. So assuming this simple example have 3 requirements, which is, say, the first one is robot shall complete the fruit picking successfully with probability at least 0.8. And we'll be able to specify this requirement into the PCTR property that a current parametric or probabilistic model checker can take. Then we will have a 3 list of requirements. The second one is related to how long, the time, then the third one is related to the energy. So again, after stage 1, we will be able to derive the algebraic expression for the requirement 1 and 2 and 3, and we realize they actually contribute by 8 parameters. And in runtime, we take a close monitoring of those 8 parameters. And for example, there's the alpha, beta, and T1, T2, and 2, E3. So we will hold the historical value of those values, and we use those values to predict the future values in a linear ways. Then we using a predicted value to propagate through the algebraic expression, which we derived in stage 1 to see how the requirements will go in the future. So, oops. So here we shows that we have a property 1, 2, and 3, and using the predicted value that we derived in the previous slides, we actually see the violation of the requirements would occur at this time point where we currently now here. And for property 2, will violate at this particular point where we currently now here. And for third one, will violate here. And in comparison, we see that the earliest violation of requirements is property 1, followed by property 3 and 2. And we can make actually adaptation decisions between now and before that to see whether we need to do something or wait for a little bit further, because the more information we're coming, we have a better prediction of the violations, and this may keep updating. But this is just a first attempt in how we can aim for proactive adaptation before it actually happens. But no means this is going to be a complex, complete process. Right. So having said that, we've touched a little bit of each part of this design as a highlight in orange, but we're still facing many challenges. So for proactive adaptations, we felt like predicting different modes of changes are important. Some are easier, some are more difficult, and predicting changes for different systems are also difficult. So for example, in our case study, we only look at a linear degradation of the system parameters, but in more advanced scenarios where servicing robots interact with humans, try to predict the human behavior is much more challenging. And understanding the root cause of these changes are important because that guided how we can solve the root cause and correct the changes. And for data collection and processing, we identify the context awareness is important, and we need to make sure what system awares what context it is in, and using appropriate analysis method are important, and to understand the consequence of such method. And we are aware that different strands are looking at similar issues that they call explainable AI. They try to interpret the meaningless of their AI results. And also for the verification engine, it is important to improve the usability to verify larger and more complex systems than what we currently can do, and improve runtime efficiency further, and to scale the runtime verification engine to even more application domains to have a generic design is also important and a challenging task. And as I said, for this, no means to be a complete design or framework to guide the trustworthy autonomous system. We probably need highlight all the pieces in order to we have a good trusted autonomous system. And that is my talk. And thank you very much.
Thank you for the nice, insightful talk, Xinwei. If people have questions, then I'm sure Xinwei will try to answer them. So, any questions? Sinem.
Yeah, thank you. Thank you, Xinwei. It was very insightful presentation. I was wondering the part about the fragmentations. So you were saying something that in the previous work, there are like domain knowledge needs to be provided by the user. To be able to have these fragmentations. But in this novel work, you have some proactive, so you were saying something like proactively dividing them into fragments. So what kind of inputs do you need for the fragmentation? So is it like the graph structure itself, or do you need additional input from the domain knowledge experts?
Yeah, thanks for the question. So for that particular work, we only need a graphical structure of the model itself, and it will only be able to start with a random node and to grow to a fragment until a valid fragment is found. It will definitely have limitations. For example, the size of the fragments could be sensitive to what the starting node is. So they may not ending up with a ideal fragment. That is, we only have one extremely large fragment and ending up with few small fragments. So it's a limitation of the current method. But in terms of input, we only need a graphical structure.
Okay, maybe a related question to this question is like, did you observe any specific patterns that this method has these limitations? Can you identify some patterns of this graph structure that you can say, okay, maybe this method doesn't work for this type of graphs or works very well for this type of graphs?
Yeah, so if a graph have many loops, which is going backwards and output, then the fragmentation is more difficult to handle. But it still be able to do that. The question is, we don't really know the criteria of being a good fragment. Ideally, we don't want it to be too big or too small, but how is good? We don't have a good definition on that. Yeah, but the assumption is if the fragment's too big for the current model to be handled, then the smaller size of it is more likely to be able to be handled. And okay, this is only the step we've taken. There's still a future work, need to look at more things as you suggested.
Thank you.
Grisel and then Michelle.
Hi, Xinwei. Thank you so much for the talk. Very interesting.
Yeah.
I was wondering, is this type of method ready to be incorporated to model checkers that are already used by the community? Because I can see how this would ease the computational expenses of existing tools.
Yeah, so this work is complementary to the existing methods because we break down the large model into small ones. So each small ones we send it to the existing model checkers. And it's also independent to the existing model checkers. So it's like if a model itself is being too big for a current model checker to handle, then we just truncate to a small pieces. And each smaller ones, we believe we'll be able to handle that one. But still, the limitation is if the smaller fragment is still too big for the current model checker to handle, then that is in the scenario where this method does not work.
Okay. Another question is, you're referring to parametric models. I wonder if this is just like a generalization of normal DTMCs, for instance? Or why does this needs to be specifically parametric?
Yeah, so because the methodology for analyzing these two types of models are different. So if it's traditional DTMCs, then it's just a straightforward calculation. But if it's a parametric where some of the transition parameters were encoded as parameter values, once in the loop, the calculation is not straightforward. They need a some approximation to calculate that. So that's why that is different. And for the process of approximation is more costly. That's why it's ending up with a rational functions. So it's something over a polynomial over another polynomial. So if I try to show, I don't know. So just because the nature of calculating it, the expression would just look like this. So it's a polynomial over a polynomial. So it's a rational function.
Okay.
Yeah.
Thanks, Xinwei.
Yeah. Can you hear me, Xinwei?
Yeah. Yeah.
Yes. Hi, Xinwei. Thank you for the presentation. It was a very nice talk. So I have a quick question. I think at the beginning of the presentation, you were discussing about the main problems, which were the data. I think you mentioned the data and the non-linearity of the data. So I want to ask if the solution that you are proposing here is, I guess it's going in the direction of dealing with the verification of the data, but I want to know if you are doing something about the non-linearity and if you can explain this a little bit.
Yeah, in this particular work, we are not specifically to tackle the issue of non-linearity caused by machine learning. This is just one of the few challenges why having a verification engine is difficult and why assuring autonomous system is difficult. And we're saying again, for non-linearity issues, where when we create the algebra expression for the models, let me find the slide where I don't know. So for that expressions, we actually be able to looking at how the Q, P and Q values are dependent and whether they are linear dependent or non-linear dependent. And we can perform a different sensitivity analysis using this algebra expression to avoid, but there's no means that we could guarantee to reduce the non-linear impact of non-linearity. So we just provide a solution to look at the interaction between parameters.
Thank you, Xinwei.
Anders?
Yes. Hello. Hi, Xinwei. Thank you very much for this interesting talk. I have a question about the fast PMC and slide number 32. I wonder, I think you mentioned that the this fast method, okay, no, sorry, not this one. So I took the wrong number. So you mentioned that you generate a similar closed form expression by using this fast PMC, right? I wonder, how do you simplify the expressions from the fragments when you combine them? Because the way I understood it is, from the fragment, you calculate the expression for that specific fragment, and then you use this fragment as probability for leaving out that, let's say, superstate into the other fragments. Then how do you simplify them? They both
right. Yeah. Right. So you understood very well. We don't necessarily need to simplify them, because if you're looking at the values for each fragment, creates the output for that single fragment. Then that fragment as expression will be used so for each fragment, we will calculate the updated transition for those three for fragment 1, for example, right? Then at abstract value, we will use the updated value for calculating abstract models. And in return, instead of having a more larger expressions, the expression and transitions for the abstract model are significantly smaller. So in that case, all the transitions are based on the newly determined fragment output. They no longer be a single parameters, they will be the expressions. But since this abstract model are significantly smaller, the calculation for this would just be straightforward. They become the multiplication of the output of fragment 1, multiply the output of fragment 2. So leaving the abstract model expression smaller, then that is combined. When you have a parameter value of original parameters, you first need to go through those transitions to derive what's the output of these values. And since the calculation derives the process, you just need to propagate the value through here. So it's just like a propagation of the value.
Yeah, this propagation procedure, would it reduce the number of mathematical operations in the abstract form? Because the abstract expression is multiplication of the output of basically the expressions from the fragments, and each fragment itself, it's multiplication of the probabilities of the transition within that fragment. But
that's correct.
In this order, I fail to see how will you reduce the number of mathematical operations in the abstract model.
In terms of that result, the difference would be, because we'll be able to analyze the big one into the small ones, then that's equivalent to consider you have a big, large expression, you'll be able to factorize into a chunk.
I see.
Then each chunk is actually a fragment formula, and you don't need to combine them all together, because in the calculation, what you only need to do is calculate the fragments. So once the output is ready, it got a fragment output, right? And abstract the output. What you need to do is calculate fragment output independently, and then you calculate the propagated abstract model, because abstract model is with respect to the output of that. You've already calculated them independently. Then when you assemble that once, you are less likely to take, you take less time to compute that expression. And in theory, it's smaller because, as I said, it's similar to you factorize the big ones into small ones because you dealt with them independently.
Yeah, I see. Yeah, thank you very much. Can I add just one more question?
Yeah, sure.
I think we have time for one short question indeed, Anas, and then another maybe short question from Colin. And
okay. Yeah, it's kind of a general question. How do you apply these model checking methods into checking whether these environment sensors, like how would you check the functionality of this environment sensors using this model checking algorithms?
No, we cannot check the functional behavior of the system. What we are interested is a non-functional behavior system. That's why our input model is a stochastic models. We're looking at the stochastic behaviors. It's not functional. So, for example, the probabilities of the transition probabilities, we probably derived it by measuring the performance of the system for a million times. Then how likely it's going up and how likely it's going down. And the individual extreme values will not affect the result of here.
Yeah. Yep. Thank you very much. Very interesting talk. Thanks.
Colin?
I think they just answered the question I was going to ask. How practical is it to derive such a stochastic model from sensors? And I think you just answered it. You basically do a number of executions and infer a stochastic model. Is that essentially it? Yeah. Okay.
Then that's fantastic. So we are finishing a minute and a half late, but thank you so much, Xinwei, for the interesting talk, and everyone for participating in this discussion. And see you at another seminar soon. Thank you.
Yeah. Thank you. Bye.